Welcome back, dear friends. This is to discuss another multi-pressure system with two evaporators, and a compressor is individual compressor system. By individual compressor system, we mean for each evaporator there is a compressor. So for evaporator 1, there is a compressor 1. For evaporator 2, there is a compressor 2. So this is called as a individual arrangement of compressor, and there is an individual arrangement of expansion valve. This is the expansion valve for this evaporator, and this is an expansion valve for this evaporator. Okay, so let us look at this schematic. What happens here? This is a three pressure system. Highest pressure is the condenser pressure. The lowest pressure is the evaporator 1 pressure, and there is another evaporator which is at some slightly higher pressure than the evaporator 1 pressure. So we'll call it as an intermediate pressure. So this way it is a three pressure system, and we will make an assumption that the refrigerant, as it evaporates in evaporator 1, it emerges out as saturated gas, dry saturated gas, meaning it is not superheated. That is an assumption we are making. Similarly, the refrigerant which is evaporated in the evaporator 2 is also a dry saturated gas. So state 1 and state 3 are dry saturated gas. So if you want to represent such a scheme on a pressure enthalpy diagram, you see that this is the state 1, which is dry saturated, and this is the state 3, which is dry saturated. State 1 is at the evaporator 1 pressure. This is the pressure corresponding to state 1, that is it is the pressure of LP evaporator, and this is the pressure corresponding to the evaporator 2. This is the pressure corresponding to evaporator 2. Okay. And this is the condenser pressure. This is the condenser pressure, right? So this is the evaporator pressure line. Evaporator 1 pressure line, evaporator 2 pressure line, and this is the condenser pressure line, right? Now what happens is, the refrigerant, as it enters the compressor 1, it gets compressed up to the condenser pressure. Similarly, the refrigerant, as it enters the compressor 2, it gets compressed up to the condenser pressure. And both of them, that is after compression, they are at condenser pressure, and the condenser pressure entry, okay, is superheated. So this is superheated. As it enters the condenser, it gets desuperheated and then finally condensed. Let us assume that there is no subcooling, so it is saturated liquid. So state 5 is a saturated liquid. So let me show you on the pressure enthalpy diagram. As it enters the compressor 1, it gets compressed up to the condenser pressure. Similarly, the refrigerant, as it enters the compressor 2 from the evaporator 2, it gets compressed up to the condenser pressure, and we are assuming that the compression is isentropic in the theoretical cycle. The entropy remains constant. They get mixed and then they get into the condenser, and we are assuming that there is no subcooling. So the refrigerant after condensation becomes a condensate, and this condensate is saturated liquid. Okay, this is how we have discussed state 1, state 3, state 2, state 4 and state 5. Now what happens next is, the refrigerant, which is a saturated liquid, it is expanded in this valve. Let us call this as EV2, and this is called as EV1. So it expands in EV2 up to state 6, and this is an isenthalpic process. Enthalpy remains constant, throttling. Okay, enthalpy is constant. Similarly, it expands from 5 to 7. Isenthalpically, it's a throttling phenomena. So 5, 6 and 7, the enthalpy is the same. Okay, this can be seen clearly from the pressure enthalpy diagram. 5 to 6 expansion and 5 to 7 expansion. So you see the enthalpies at 5, 6 and 7, they are same, 5, 6, 7. So this is a vertical line. This is a vertical line. Okay, and then they enter the respective evaporators. From 7, it is wet, it enters the evaporator and comes to state 1. 6, it enters the evaporator 2 and comes to state 3. Okay, 7, it evaporates to 1, 6, it evaporates to 3. So this is the schematic and the representation of the multi-evaporator system, wherein there are individual compressors, right, and individual expansion valve. So this becomes the arrangement. Now how to solve these numericals? So generally the capacities of this evaporator 1 and evaporator 2 would be given. Let us call them as TR1 and TR2, and that would help us to calculate the mass which is flowing through evaporator 1 and evaporator 2. So let us call the mass flowing through evaporator 1 as M1 and mass flowing through evaporator 2 as M2. So M1, how do you calculate? M1 is total refrigerating effect into 3.517. Why I am multiplying it with 3.517? Because I want the answer in kgs per second. If I want the answer in kgs per minute, I need to multiply this with 211 or 210. Okay. Now, similarly, if you want to find M2, I need to take TR2 into 3.517 and enthalpy difference across evaporator 2. So M1 you find as TR1 upon enthalpy difference across evaporator 1, that is H1 minus H7, and M2 you find it as TR2 and enthalpy difference across evaporator 2, that is H3 minus H6, and you multiply this either with 3.517 or 211. Multiplied with 3.517, you will get the mass flow rate in kgs per second. Okay, if you multiply it with 210, you will get it in kgs per minute, right? And then once you get that, you can find the total compressor work, which is a summation of this compressor 1 and compressor 2 addition. Get the total compressor work and divide it by the this would be in the denominator, and refrigerating effect upon compressor work is the coefficient of performance. So this is how we solve the numericals on two evaporator system with individual compressor and individual expansion valve. I hope that this is very clear to you. Only thing to be understood is here the compressor work is addition of two compressor valves. Okay, in two, if the compressors are 2, if there are 3, then it is addition of 3 compressor works, right? Thank you very much.